Have you ever thought about how you could unmix something? I mean, it sounds kind of impossible, doesn't it? Well, today, we're going to dive into the world of chemistry to solve that exact puzzle. We're going to decode the science of separating mixtures, all by looking at this one simple drop of black ink.
You know, like in any good detective story, our main clue isn't really what it seems. That plain little black dot on a piece of paper? It's actually hiding a whole secret world of color, a chemical story that we're about to uncover together. So, that's the big question, right? What is the real story behind this black ink? Let's, put on our imaginary lab coats and use the tools of chemistry to find out exactly what's hiding inside.
Okay, so the first thing you've got to know is this. Black ink isn't just one single black substance. Nope, it's almost always a mixture of different colored dyes. And lucky for us, chemists have some really clever ways to peek inside and see all those different parts.
So our first tool is something called paper chromatography. Now, I know the name sounds super complicated, but don't let it fool you. It's basically just a simple but really powerful way to separate all those different hidden dyes based on how they move through paper. So how does it actually work? Well, the best way to think about chromatography is like a race for colors. We're going to set up a little racetrack on a piece of paper and see which of the dyes hiding in our ink is the fastest. And this isn't just some fun classroom trick. It's the same basic idea used in forensic labs to analyze evidence from crime scenes. Pretty cool, huh? Every race has two main parts, right? First, you've got the racetrack itself, in this case, the paper. In chemistry, we call that the stationary phase because, well, it stays put. And then you have the thing that makes the race actually happen, the solvent, which for us is just plain old water. We call this the mobile phase because it moves and it carries the dyes along for the ride. And setting up this race is super easy. You just take a piece of filter paper, draw a line in pencil near the bottom, then you put a tiny, concentrated dot of your ink right on that line. After that, you hang the paper in a beaker with a little bit of water, making absolutely sure the water level starts below your pencil line. As the water starts to climb up the paper, the race begins.
Now hold on, here's a really important detail. Why do we have to use a pencil for that starting line and not, say, another pen? What do you think would happen if we did?
And the answer is actually pretty clever. Pencil graphite is insoluble, which is a fancy way of saying it won't dissolve in the water. It just stays put. But if you used a pen, the ink from your starting line would jump into the race too, smearing all over the place and totally ruining your results.
Okay, so you wait about 20 minutes, the race is over, and what we have now is called a chromatogram. Now comes the fun part, learning how to actually read this thing and figure out what it's telling us. The very first thing we do is mark the finish line. In chemistry, this is called the solvent front. It's just the highest point the water managed to climb up the paper. We just draw another little pencil line right there to mark it.
And boom! Look at that! Our single black dot is separated out into all these different colored spots. This happens because some dyes dissolve in the water better, or they don't stick to the paper as much, so they travel further and faster. This beautiful separation proves it, right there. Our black ink was never just black, it was a mixture all along.
Now, to make this all scientifically official, chemists calculate something called the RF value, which stands for retention factor. The easiest way to think about it is like a unique chemical fingerprint for each dye. It lets scientists anywhere in the world identify a substance just by calculating this one simple number. And the formula to find this fingerprint is super simple. The RF value is just the distance the dye traveled from the starting line divided by the distance the solvent traveled from the starting line. That's it. It's a simple ratio, but it's an incredibly powerful tool. So, for example, let's say a pink dye in one of our experiments traveled 59 millimeters, and the water, the solvent front, reached 64 millimeters. You just divide 59 by 64, and you get an RF value of 0.92. That number is a constant, a fingerprint for that specific dye under these specific conditions. Okay, so we've cracked one part of the mystery. We know our black ink is really a mixture of dyes. But what about the clear liquid that they're all dissolved in? To separate the water from the dyes, we're going to need a whole new tool, simple distillation.
Distillation basically works by taking advantage of boiling points. We gently heat up our ink. The water, which boils at 100 degrees Celsius, turns into steam and leaves all the colored dyes behind. That steam then travels through a tube, gets cooled back down, turns back into pure liquid water, and drips into a separate container. Voila!
Now you might notice in a lot of lab setups, the test tube that's collecting the water is sitting in a beaker of crushed ice.
Why go to all that extra trouble? What's the ice for?
It's really all about being efficient. That ice bath makes the surface of the test tube super cold, which forces all the hot steam that hits it to cool down and turn back into liquid really, really fast. Without it, some of your pure water might just escape as steam, and you wouldn't collect nearly as much.
All right, running these experiments yourself is a ton of fun, but it does take some precision and, more importantly, some safety. So let's go over a few pro tips right from the lab to make sure you get great results and, don't cause any accidents. Safety first, always. Make sure you clamp your flask so it can't tip over. Double-check that the delivery tube isn't blocked, because that could cause a dangerous pressure buildup. And when you're heating, always be ready to move that flame away if things start boiling too wildly. And seriously, remember, the glass is going to be 100 degrees Celsius. That's boiling hot. So don't touch anything until it's had plenty of time to cool down. There are also a few common mistakes to watch out for. With chromatography, if your ink dot is too big, you'll just get blurry, smeared colors. With distillation, if you heat it too hard, the ink can actually bubble and splash over into your collection tube, which ruins your pure water. Oh, and make sure your seals are tight or all your steam will just escape into the air.
So, there you have it. The mystery is solved. Using chromatography and distillation, we proved that our simple drop of black ink is really a mixture of different colored dyes dissolved in water. But why does any of this really matter? I mean, it's bigger than just ink.
These techniques, these methods of separation, they're fundamental to pretty much all of science. How we purify drinking water, how we refine oil into gasoline, how forensics teams analyze evidence. They let us break the world down into its most basic parts, so we can understand how it all works. Which leads me with one last question for you. What everyday thing would you want to take apart, just to see what it's really made of?